Hey chemistry peeps, Jess McCartney here. Today we're going to start looking at green chemistry principles and getting to know how carbon dioxide affects and being able to calculate the carbon dioxide amount when we're looking at combustion reactions. So measuring your carbon footprint allows you to determine carbon reduction opportunities, usually linked to energy transportation. So when energy is produced, lots of energy is actually lost through this process. And so as chemists, we can start to think of ways to preserve this energy or use this energy at different parts. And this is the very beginning at starting to look at those green chemistry principles. So let's get started. So we're going to be looking at calculating energy changes from combustion reactions. So the study design dot points for this lesson, we're going to be looking at mass-to-mass calculations involving combustion. So that's this one here. Mass-to-volume calculations, volume-to-volume calculations, and last but not least, determining heat energy released and reactant and product amounts, net volume of mass greenhouse gases, which is carbon dioxide, methane, and water. So when we're looking at stoichiometric calculations, this is a nice flow chart to look at. So you can see that the beginning, depending on what you have, so you may have energy, mass, or volume at the start, and depending on what you have at the start will depend on the formula that you use. So you have your energy formula, mass over molar mass, and molar volume formula. Then you will work through your stoichiometric ratios. Remember using your unknown over known. And then depending on what the question is asking you, what you need to find. So it could be energy, mass, or volume again. One neat little trick that we are going to look at today is just looking at the stoichiometric ratios when we're going volume to volume, and I will show you that further on. But this is a nice quick way to eliminate lots of the calculations in our questions. So mass-to-mass calculations, we have done this a lot in Year 11, so nothing has changed. This is lots of revision for all of you. So remember, when we're looking at the amounts, we are talking about the number of mole, and this would be the known. So when we have the masses of our initial calculation, so that could be the products or the reactants, depending on what you're trying to find, you would then convert the masses into the number of mole using the mass over molar mass formula. This should be hopefully ingrained into your brain already. This is useful for not only determining the carbon dioxide and water released, but we can also start to think about the energy in complete combustion reactions. So that's where we can continue to use these. So let's look at a worked example. The question is, calculate the mass of carbon dioxide in kilograms. So really important to note that our answer needs to be in kilograms. When 340 grams of butane, the formula is given to us, burn completely in oxygen. So that means that is a complete combustion reaction. So the first thing you need to do in a stoichiometric calculation is you need to write a balanced equation. Some questions are given to you, some don't. So this is an example where the question has not given you the equation and you have to be able to write it. The question has told you the formula for butane, so that does make the start nice and easy. So we have butane, C4H10, right here. It's reacting with oxygen because it is a combustion reaction. And in a combustion reaction, in a complete combustion reaction, it will always produce carbon dioxide and water. Hopefully you know how to write these equations already. When you're balancing the equations, remember to start with the carbon first. So we have 4 carbons here. So initially we would put a 4 on this side. So I'm just going to show you how to balance it out completely. Then we're going to look at the hydrogen. So we have 10 here. We have 2 here. So we're going to put a 5. And then if we look at the oxygens, we have 4 times 2, which is 8 altogether, and 5 times 1, which is 5. 8 plus 5 is 13. So this makes it uneven. Now, generally, we don't like to do half balances, and that's why we've put a 2 in front. So if you notice the 2's in front here, that means that will double that to 8, which is listed here. That will double that to 10. And then if you add them up, 8 times 2 is 16, plus 10 is 28, and that means we can put a 13 in front of that O2. So that's a balanced equation. It's really important that we balance our equations correctly because in a stoichiometric calculation, we need to be able to use those ratios to get the unknown. So the next step is to calculate the number of mole, and this is a mass to mass calculation. So we're going to begin with the mass. So we have the mass of butane, 340, divided by the molar mass. Now remember, the molar mass is the atomic masses added up. So it will be carbon, which is 12, times 4, plus 10 hydrogens, so plus 10, and that would equal 58. Then you can do 340 divided by 58, and that gives you 5.86 mole. Now we're going to do our mole ratio. Now this is the unknown over known. The unknown is what we're trying to find. So the question has asked us to find the carbon dioxide. So we look at our coefficients in the equation, so the equation that we just balanced. Carbon dioxide is 8, so our unknown is 8. Our known is what we were able to calculate in the previous step, so that's the butane. And you see in the equation, the butane is 2. That's where that 2 comes from. 8 divided by 2 is 4. So that is our ratio. Now the next step is calculating the mole of carbon dioxide. So we use our ratio that we calculated above here, which is 4, and we times it by the mole that we know. And so the known is butane. So that's 5.86. So that's from step 2. And that gives us the mole of carbon dioxide, which is 23.45. The last step is calculating the mass. Now remember, the question has asked us in kilograms, so we must convert at the end. So the mass is rearranging the mole formula to make it mass equals mole times molar mass. So it'd be 23.45 times the molar mass of carbon dioxide, which is 44. And that gives us 1,032 grams of carbon dioxide, because our mole formula is always in grams. So to convert to kilograms, we would divide by 1,000, and that gives us 1.03 kilograms. So when we're looking at the marking guide for this, you do get 1 mark for writing the balanced equation. You only get the mark there if you have to write an equation. So if the equation is given to you, this mark will obviously not be there for the stoichiometric calculation. You get 1 mark for calculating the butane or the known, 1 mark for calculating the mole of carbon dioxide, and that is with your stoichiometric ratio, and then 1 mark for calculating the mass of carbon dioxide, but only in kilograms. So if you only went to grams and did not convert to kilograms, you would not get that last mark. When we are looking at substances that are in standard lab conditions, and so if they are, then we can use the molar volume formula, which is this one here, and that's only when the questions state that the conditions are at SLC that we can use that. Remember, the VM constant is found in the data book, so remember to double check your data book if you're not sure. So they're the 2 formulas that we're going to be using here. So let's have a look at an example. Calculate the volume of carbon dioxide in litres produced when 2.00 kilograms of methane is burned completely in oxygen. The gas volume is measured at SLC. So we have a bit of information here. Obviously, we have the original mass that's in kilograms, so we know that we have to have a conversion there into grams. It's asking for the volume in litres, so that should be nice and easy because we know our formulas are already in litres. So at the end, there should not be any conversion. And the question states that it's at SLC, so we know that we're going to be using the VM constant at some stage during this calculation. So the first thing we need to do in this particular question is write an equation because it is a stoichiometry calculation. So we have methane. The formula for methane is CH4. So then it's going to be reacting with oxygen, which is O2, and it's a complete combustion reaction, which it says. So it's going to be producing carbon dioxide and water. So to balance out, remember to start with the carbon. So we have 1 carbon on the left in the methane, 1 carbon on the right, so that's nice and balanced already. Hydrogens, we have 4 hydrogens here. We have 2 hydrogens in the water, so we're going to put a 2 in front to balance out the hydrogens. And then we have oxygen, so we have 2 oxygens on the carbon dioxide and 2 oxygens on the water. 2 times 1 is 2, so that's 4. So we're just going to put a 2 in front of that oxygen. So that's a nice easy one to balance. So the next step is to calculate the number of mole of our known. So we know the mass of methane. Don't forget to convert it to grams. So we have 2 kilograms, so it's going to be 2,000 grams. So that's what that is. We divide it by the molar mass of methane, which is 16. So that's 1 carbon, 4 hydrogens. Put that in the calculator and we get 125 mole of methane. Next step is to do the stoichiometric ratio. So it's unknown over known. The unknown is carbon dioxide. There is nothing in front of that in the equation. So just here, so that means that's a 1. So that's where that 1 comes from. And the known is the methane, as that's what we were able to calculate in step 2. And there is nothing in front of that as well. So that is also a 1. So it's a 1-to-1 ratio. It makes our calculations super simple. That means that the mole of methane is equal to the mole of carbon dioxide, which is 125 mole. So the last step to the calculations is to calculate the volume, as that is what the question has asked us to do. So we're going to do the volume is equal to the mole, which we just calculated in step 4, and then times it by the molar volume because it's at SLC. The molar volume found in your data book. So we have 125 mole times by 24.8. That is the constant found in the data book. Put that in your calculator and you get 3,100 litres. So it's important to put your answer into significant figures. So if you have a look back at the question, the value that's given to us is in 3 significant figures, which is here. So our answer should be in 3 significant figures. So we're going to put into scientific notation. So if we have our decimal point here, what we're going to do is we're going to move this back 3 places, remove the last 0 because that will then be in 3 significant figures, and then we're going to put it as 10 to the 3 as we've moved the decimal place back 3 places. And don't forget your unit as litres on the end there. The marking guide here, this would be worth 4 marks. So we have 1 mark for a balanced equation, 1 mark for calculating the mole of methane, 1 mark for calculating the mole of carbon dioxide alongside your mole ratio there, and 1 mark for calculating the volume in carbon dioxide. In a VCAR exam, they only choose 1 question to take off marks for significant figures, but you don't know which one that is. So it's just a good practice to start to putting all your answers in significant figures, just so you don't lose that easy mark that you don't have to lose. So we have another worked example here. This is going to be using a different formula when we're looking at volume. So it's calculate the volume of carbon dioxide in litres produced when 300 grams of propane burned completely in oxygen. So it's very, very similar. The only difference that we have here is that we have conditions that the reaction is put under, and the conditions are that it's at 60 degrees and it's measured at 200 kPa. So unlike the question before where was that measured at SLC, we actually have different conditions here. So this means we have to use a different formula. The steps are the same. So the first step is we're going to be writing a balanced equation. We have propane now, so propane is C3H8, so remember to take a look in your data book if you're not sure. It's reacting with oxygen. It is a complete combustion reaction, so it produces carbon dioxide and water again. Remember to start with your carbons when you're balancing. So we have 3 carbons here, so we're going to put a 3 in front of the carbon dioxide. Hydrogens, we have 8. We have 2 on the water, so we're going to put a 4 in front to make the 8. Then we look at oxygens next, so 3 times 2 is 6, plus another 4 is 10, so we're going to put a 5 in front of that oxygen. So the next step is to calculate the mole of our known, which in this case it's propane. We've already been given the grams, so we don't need to do any mass conversions here. So 300 grams of propane divided by the molar mass of propane, and it gives us 6.81 mole. The next step is to calculate the ratio, so it's unknown over known. The unknown is what we're trying to find, which is carbon dioxide. So if we look at the coefficient of carbon dioxide, it's 3, so that's where that 3 comes from. The known is what we're able to calculate in step 2, so that is propane, and that there is nothing in front of that, so that means that's a 1. So it's 3 over 1. The next step is to calculate the mole of carbon dioxide, which is your unknown. So you're going to use the ratio from step 3, which is that 3 over 1, times by the mole of the known, which is 6.81. So this is the mole from step 2. And then that gives you 20.45 mole. The last step is to calculate the volume, so actually answer the question. Now, like I said, because there are conditions involved here, we actually have to use the PV equals nRT formula and rearrange to find the volume, which is what we've done here. So volume is equal to nRT over P. So we're going to put all our values in. So the mole is what we calculated in step 4, so that's 20.45, times by the R, which is the constant found in your data book, 8.31, which is that one there, times by the temperature. Now, the temperature is needs to be in Kelvin, so you need to add the 60 degrees to 273, and that gives us 333. And divided by the pressure is already in kPa, so we do not need to do any conversions here. So that's going to go straight as it is. Put it all in your calculator, and you get 20.83.01 litres. Again, we're going to put this into significant figures. So what we're going to do is we're going to remove the last decimal places there, and we're going to move this decimal place over 2, just to put it into nice scientific notation. So that gives us 2.83 times 10 to the 2, because we've moved the decimal place 2 times, and it's still in litres. The marking guide is similar to before. You have 1 mark for balancing the equation correctly, 1 mark for calculating the mole of the propane, which is your known, 1 mark for calculating the mole of carbon dioxide using your ratio, and 1 mark for calculating the volume of carbon dioxide that the question has asked you to do. So looking at volume to volume calculations, this is actually a little bit different to what we've done before, because we can sometimes assume that all the volumes are in the same conditions going from the reactants to the products. So when we are doing this, we can actually skip lots of the mole calculations, and that we can actually go straight using the mole ratio to calculate the unknown volume. So this makes it actually a lot easier in terms of these calculations. Now remember, this is only true for reactions that are kept at a constant temperature and pressure from reactants to products. If there is any change in temperature pressure, then this particular process will not be able to occur, and you do have to use the steps that we've done in the previous questions. But I'll show you what this looks like when it is kept constant. So let's have a look at a worked example. Calculate the volume of carbon dioxide produced when 3.2 litres of ethanol is burnt completely in oxygen and the pressure and temperature is kept constant. So looking at this, we can do a nice easy calculation as the pressure and temperature are all kept constant. So let's have a look at the equation first. So the equation is looking at ethanol C2H5OH, which is here. It's completely reacting with oxygen, so we have O2. As it's completely reacting, it's going to produce carbon dioxide and water. Then we're going to balance out this reaction. So looking at carbons first, so we have 2 carbons here, therefore 2 carbons will be there. Looking at hydrogens, we have 5 plus 1 is 6, so we need to do 3 times 2, which is 6, so we're going to put the 3 in front of the water. And the last step is the oxygens. So we have 1 oxygen here on the left side, which is that one, and we have 3 on the water and 4 on the carbon dioxide, so that's 7 altogether. Now, we do need to have 7 on both sides, but because we have 1 already in the ethanol, which is that means that there needs to be a 3 in front of this oxygen, which will make that 6. 3 times 2 is 6, plus 1 more is 7. So that is balanced. Then we're going to look at our ratio, which is unknown over known. The unknown is the carbon dioxide. There is a 2 in front, so that's where that 2 comes from. The known is the ethanol, which is that. There is nothing in front, so that means that's a 1. So that makes that a 2. The volume of the unknown is equal to the mole ratio, which we just calculated here, which is 2, times by the volume from the question, 3.2. That gives us 6.4 litres. The mark allocation for this is correctly balancing the equation, so this part here. And then the second mark is calculating the volume of the carbon dioxide, so that's these two steps here combined. So when we're looking at calculations involving energy change, we're going to be looking at the thermochemical equation, and this is a given reactant and a given product that's produced. When we have that, we can actually use that to calculate the total amount of energy released in a combustion reaction. Using the molar heat of combustion to determine the total energy released in the reaction according to the formula. So the energy release is equal to the molar heat of combustion times by the mole of the fuel. Now the heat of combustion is found in your data books. So the tables that we have here are similar to the ones that are found in your data book, and this gives you the molar heat of combustion, either in kilojoules per gram or kilojoules per mole, depending on what you are trying to calculate. This will also depend on whether the substance is pure or not. So you would see all of these here in the first table are all pure, and that means that the molar heat of combustion can occur in both. And in kerosene, diesel, and natural gas, these are mixtures, so therefore that they can only occur at kilojoules per gram. So in summary, when we're looking at enthalpy change, we are using the molar heat of combustion to determine the total amount of energy. Now we're using the formula, the molar heat of combustion times by the mole of fuel. Remember to continue to use this flow chart to be able to work out which way you need to go when you're using those stoichiometric calculations, using the formulas as you need depending on the information that you've been given in the question. What we're doing next is calculating energy changes using water. I will see you then. Bye-bye.